So I understand this has been a very long day for you, and I'm sure it's going to be a little bit longer. So I really appreciate your presence here. Sorry for attracting your attention. Let's move on with the material we have to finish for the 1 hour. We're going to be 45 minutes. We're going to be together. Just to remind you, we're still in the portion of the course where we're doing C2 assembly, and we're going to be continue our discussion about subroutines. And today we're going to do a few more examples. In particular, we're going to do a recursive function. I didn't write that stuff. No idea what they are. Yeah, this is stuff that I forgot a long time ago. I'm not quite sure I even learned them at some point. Anyway, where were we? We're going to be doing subroutines. We're going to do a recursive subroutine as means of practicing our skills with routines. The exact function itself is not, it's immaterial. I'm just picking up one of them. There is a function named after a person, and it's a mathematical function. We're going to see its imperative implementation in C. This is the Ackermann function. So it's something like this. And Ackermann now in, yes, Ackermann, okay, good. Just because I don't like to write a lot, let's do what usually they do in North America. So let's condense the name of the person, make it Ak, okay, good. What is this function? It takes two arguments, int x and int y. And there's a calculation underneath. Anybody is familiar with this function? Every year I keep asking this question. If you were familiar, I would ask if you know what it's used for. I have no idea. All I've found so far is that it grows very fast. Anyway, so there's apparently some use for that. And it just shows my ignorance that I don't know why the uses might be. So it's like a three-case statement, that function. It says if x happens to be 0, then please return y plus 1. Now, if that's not the case and y is equal to 0, then return Ackermann. So call yourself again, but this time around, call it with s. So x starts decreasing and y disappears, becomes 1. Okay. Otherwise, if none of the above holds true, return Ackermann with x minus 1, so decrease x. And now, for the big surprise of the function, one of the arguments is going to be Ackermann itself, again, with x, y minus 1. Now, this is the function. Why is the function like that? Maybe there's a good reason. We don't care. We're going to play the role of the compiler. We have to write assembly that implements this. Right? That's our role right now. It's not to question why is it like that or why is it like this. That's not it. This is a blueprint for us. We're just being tasked to implement it. Okay? Now, let's talk a little bit about semantics. What does this thing mean? Right? How do you interpret that? In C and in many programming languages, anytime you have a function call, the sequence of events is as follows. First, you evaluate the arguments, and you get values for them, and then you call the function, which is to say that this is really equivalent to writing the following. Temp1 equals x minus 1. Temp2 equals Ackermann x y minus 1. And then call Ackermann with temp1 and temp2. Okay? This is what it means in time. This is syntax. This is semantics. Everybody okay with this? So this is what we have to implement at the end. So don't get confused by this construction here. This really means do this, do that, get two values, pass them as arguments to Ackermann. That's what it means. One of them happens to be a call to a function. Who cares? We just do the call to the function. Any question about what we need to do? I'll take silence as a no, and not as a no idea what you're talking about. Okay, let's move along then. And let's try to write the function. So we're going to start writing assembly now. This is always fun. Okay, we put a label there, that's the function. First question we ask anytime we write a function. Does Ackermann call a function? The answer is a 3-letter word.
Yes.
Yes, excellent. I don't know how you come up to that conclusion, but that's excellent. Okay, so if you got to call a function, this means that you have to use the call instruction, most likely, which means you're going to destroy array. Hence, your prologue and epilogue have to save and restore, respectively, RA. So first thing we do is add I, SP, SP minus 4, store word, RA, 0, SP. And eventually, there's going to be an epilogue somewhere. And there we're going to have to do load word RA 0 SP. Add I, this is fun, SP plus 4 and return. So we wrote this, we're done, nothing to worry about. So all we know now is that when the function is being called, its stack frame is going to contain at least one value, which is the array. As we write the code, we may need to allocate more space. We're going to deal with that. What's the thing that bugs you?
What's SW?
Store word. Oh. Is it STW? Okay, thank you. This shows you that I do code every day.
In assembly.
Huh?
In assembly.
Absolutely. Yeah, no, I actually write binary. Nothing else to do, yes. I don't wish you do the same, though. Where were we? Oh, the function. Okay, so first thing, we take it by strides, right? Who cares what comes after that? Just look at the first statement, one thing at a time. If x is 0, then do something. This is the if-then statement. So remember, we're going to invert the condition to jump over the then part, because we don't have an else part here. So we're going to say, branch not equal, what is x? X is the first argument. By convention, it will be in R4. Excellent choice. And that will be a label which I will define later on. So if x is not 0, then jump over what comes after that. Otherwise, this is for us to remember. This means x is 0. And what do? What the function says, return y plus 1. Okay? So we're going to have to return something. It's going to be an addition. Add I. Where do we return values? One crowd, one voice, R2. Thank you. And what do we put there? Y plus 1. Okay, where is y?
R5.
I know when you go to concerts, you're paying the pepper people, so they should be singing. So, okay, I'll play along. R5 and plus 1. Okay, that's y plus 1. Everybody okay with this? And we're putting that into R2, which is our return value. And what do we have to do after that? Epilogue. Done. Done with the return. Everybody's happy. At least with this. So we're done with this part. Let's go to the next statement. Well, the next statement says if if y is 0, right? So now we are in x not 0. So we arrived there. Sorry, this is. And now we're just looking at, we hone on this one and we'll focus only on that statement. If y is 0, so very similar to what we've seen before, we're going to say if y is not 0, or is not equal, R5, R0, y not 0, and this we're going to complete later on. But right now, if this fails and we fall through, we are in the y is 0 case. So let's put a label there. This is only for our own reference. Doesn't mean anything to the assembler. We're not going to refer to that label anyhow. Y is 0. What do we have to do? We have to return this. Okay? Now, first we have to call the function, then return the value. Notice that the function, any function will return the value into R2, sorry. We have to return our value in R2. Nothing to do there. We just have to call it. Whatever value R2 has, is this the one we have to return. To call a function, we have to create the arguments. There are two arguments here. One is x minus 1. What is x? X is R4. So we just have to subtract from R4 1 and put it back to R4 because this is the first argument. I hope I'm not confusing you. This is R4 and this is in R5 by convention. When we call a function, this now has to become R4 and this has to become R5, okay? So let's do that. We're going to do add I, first argument, R4, where x, what is x? R4 again, minus 1. So this is first argument to the next function becomes x minus 1. Okay? Notice this is not x equals x minus 1, right? R4 contains the value of x, we're destroying x from this point on, we're losing it. This doesn't mean that, it just means pass the argument. I hope this doesn't confuse you for the time being. Hopefully it will become a little bit more clear why I'm saying that in a few moments. Why? The second argument has to be 1. That's all there is to it. This is the second argument to the function we're calling. And then we call it. After that function returns, yes please.
So last lecture we said caller saved registers is R2 to R7 as well.
Yes.
Since this function is not calling on the function, would we have to save?
If we care for the values. That's a very good question.
Okay.
Let me finish this and then we can go back to that question. And then we're going to branch to epilogue again because whatever value Ackermann returns is our own return value. Okay. So the question is the following. Since we're calling a function, doesn't matter which function that is, it happens to be a copy of us, but it doesn't matter, it could have been anything. We know for a fact that there's no guarantee that R4 or R5 will survive the call. We cannot assume that. Should we save them? We are the caller at this point. So we have to decide whether we care for the values of R4 and R5. Let's look at where we are right now. And let's understand what's going on. You're coming in, this is the entry point to Ackermann, and there is, first you say, is x equals to 0? Yes, then you do return y plus 1, and we are out, okay? Now, next question is y equals 0? This is the no part, sorry. Then we're going to do something else. We're going to do return Ackermann x minus 1, 1. And then what do? We'll go here, okay? Notice the arrow. This takes you outside of Ackermann. What's the observation here? Up to this point, R4 contains x, and R5 contains y. Do you use them at all afterwards? It's a rhetorical question. So these values, as far as you're concerned, they're dead to you from this point on. So that's why you as a caller, you're making the call. I don't care for these values. I don't have to save them. Can you save them? Of course you can. You can allocate space on the stack. You can have them there, and then you can restore them. Is that needed? No. Will that harm anybody? No. Okay. Because we don't want to just do extra work just for fun. We don't. Okay. But it could have been fine to save them. It's just superfluous. There's no actual need for it. Okay. Everybody understands the story why here we go directly to branch epilogue. We don't manipulate R2 because this guy's return value is exactly our own return value. They return in R2. We have to return R2. Well, it's what we're going to move R2 to itself. There's no point in doing that. It's already there. That's why we don't do anything with R2. And now for the, yes?
But I have a question related to what he said.
Yeah.
But we care about R4 and R5 to get like x minus 1 and
Yes,
1.
they do.
But so x minus 1 came from the x that was
Enter, yes?
So shouldn't we be saving R4?
For what purpose? That's the question you should be asking. From this point on, up to this point, you really needed to know what R4 was so that you can calculate this. From this point on, you couldn't care less what R4 was. Right? You do have the new use of R4. This is the argument to the next function. And you do have the new use of R5. You don't care what, from this point, you don't even care what y is. Okay? Good? And where are we now? And now for the grand finale, we are here. Y not 0. And this is the part where we have to implement really this. Okay? And this is a slightly different discussion now from what we're having right now with regards to whether we have to save any of the values, because I want you to observe the following now. So this is why I'm doing this function, by the way. I came up because it allows to look at all this kind of stuff. The way I have it written is not very clear, but notice that we're making a call to a function, and at the same time, we need somewhere to remember what is x minus 1. Okay. How about if I wrote this like that? What if I have written it like this? I think it's going to be clearer that way. Temp2 is Ackermann. This is this part here, okay? And underneath that, I said Ackermann now, x minus 1 plus temp2. I think this makes it clearer, even though it's exactly identical. It's the same thing, okay? Now, look at this. There is a function call here. Time goes this way, and there is a use of x here. That x is that x. So the lifetime of x extends over this function call. Am I making any sense to you? Let's view this differently now, on this diagram. We're over here now. This is neither, okay? Neither nor, okay? And now what do we have to do? First thing we got to do is temp2 equals Ackermann. What's the statement? X, y minus 1. This is the first statement. And after that, we have to do another one, which is return Ackermann x minus 1 temp2. Now everything converges to the exit. I apologize for my wonderful handwriting again. First event, second event. Look at where x appears. X appears here, great, but x appears here too, which really means that the value of x has to survive that function call. In compiler parlance, terminology, this means that the lifetime of x extends up to this point. Okay? Y's lifetime does not reach this point. Y dies here. This is the last time you care about y. Everybody care with this? This is the lifetime. X, however, is live here because we're using it, and lo and behold, is live here too. So x has to survive the call, and now we refer to the convention, which says that x, which is the first argument to us, is a caller save register. So we have to preserve x around this call. We have to make space on the stack to save the value of x, and then restore it before we do the second call for us. Does that make some sense? Okay, I hope it does. So let me implement that, and then we can ask questions. So at this point, we know we're going to have to make two calls back to back. During the first one, we have to preserve x. So got to allocate space on the stack. Add I, sp, minus 4, store word r4, 0, sp. This saves x on the stack. Since we safely have saved x, now we can destroy R4 for the time being. What is the calculation we got to do? We got to call x as pass x as the first argument, so R4 remains as is. But we have to decrement R5 because it's going to be the second argument, and this is y minus 1. So the only thing we got to do is add I, R5 minus 1. This is equivalent to y minus 1. Pass that as a second argument. It just happens that Y and R5 coincide. Call Ackermann. Okay. Now, restore R4. And now we must do the second call to Ackermann. This part. What is the first argument? X minus 1. Well, we just restored into R4 the original X, so we have to subtract that. Okay, this is X minus 1. Where is Y coming from?
R2.
Thank you. Y is the return value of the previous call we made to Ackermann. Where does this have to go? It has to go to the second register, right, to R5. So we got to do a add R5, R2, R0. And plans are made to be broken. So this thing has to be, we have to make space here. So my apologies for that. So there's one instruction that's missing in between, which is a call to Ackermann. This implements this call here. Okay. Questions now?
So immediately after the call, the last one, it will immediately fall to the epilogue?
Yes, because there's nothing else in the function, that's why. It's just convenient that it is that way. Okay. Sorry for that. Okay. Now, there are some things we can do to make this code easier to understand, if we wish. For example, rather than allocating extra space here for the stack and deallocating it over here, we could have allocated 8 spaces on the stack to start with and use it only when we needed to. What I'm trying to say here is we could have done the following. I don't have a different color. I could have done this, this. This could have been -8. This could have been +8. Okay. This would have been 4. And this would have been 4. Don't hate me for the writing. All I've done right now is I created a stack frame that has 2 spots. A distance +4 from the top of the stack is always array. A distance +0, on occasion, depending on the path you follow, I may use that to store R4. The nice thing about this is the stack frame is constant for the duration of the function. It always has 2 spots. If you are a debugger, you don't need to remember where exactly you are. The variables are always there. You can always refer to them. It's a convenience.
Can you leave it the way it was before, just for readability's sake?
Can you leave it the way? Yeah, of course, it will still do the right thing. Right? They're both functionally equivalent. The question is which does less or more work, and that's a bit more of a discussion. I mean, you can probably see in what's going on over here. In the first case, you're always allocating space, so you always use amount of memory, right? But then you don't do 2 adds and 2 subtracts. Right? How do you decide whether that's a good idea? One formula here might be what's the most common path. If most of the time you end up here, that's probably better what we've done right now. If this is a rare event, the previous thing is better because you save that extra add or whatever. Is this worth your time? Absolutely not. Not for Ackermann. For something else maybe, but not for this one. So if you really had to squeeze every tiny bit of performance for some reason, either get a better machine or do stuff like that.
It's also taking more memory when you do it that
Yes,
way.
yes, yeah.
Trade-offs, right?
Yes, but in modern machines, that memory would typically be close to your... Anyway, yes, the answer is yes, 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 yes. Absolutely, you're absolutely right. But there's always like,
Hopefully.
We're good? Move on to the next chapter. Okay, so small intermission while I do some housekeeping. And we'll talk about aggregate data structures. Alrighty then. So let's talk about sorted binary trees. Wow, that's a nice name. Sorted. That's what I'm trying to say. I don't know how it sounds to you, but that's what I'm trying to say. Sorted. And binary. Tree. Wonderful. Okay. What is this thing? It's a graph, a directed one. So you have nodes and vertices. It's a tree. So every node has a bunch of children. There are no arrows going back. So you can do this in layers. And it has a nice property. For my tree here, I'm going to assign a value to every node. For example, I don't know what I did here. Okay, let's say this is 10. And the sorted, this part, so this is the binary tree business. There is a node and it has two children, hence the binary, two of them, left and right. The sorted means the following. It has the following property. If you look at any node on the left side, you will have a value that's less than that. If you look at any tree, any node in the right subtree, as we say, it's going to be greater or equal. So for example, if I have a 5, it could be here. And over here I can have a 3. But over here I can have a 7. Okay? What's the property? Look at 10. All of these numbers are smaller than 10. Look at 5. This is smaller than 5. This is bigger than 5. Fair enough? Okay. Let's populate it this way. Let's make this 20. Let's make this, I don't know. I think this is getting too much. This is points to nowhere. It's nil, so there's nothing there. And let's make this, give me a number.
34.
34 is an excellent choice. Okay, good. Here is a binary tree. Binary trees are a rudimentary data structure, but they're very nice if you're searching for things. So if you have information and you want to quickly be able to search through it, these give you logarithmic runtimes, right? And depending on how many elements you have, if this is a very nice and balanced tree, as they say, so roughly this side and this side are equal in terms of how they look and how many elements they have, you can search through that in logarithmic time, where logarithmic is an expression of the amount of elements you have there. It's a fast way of accessing information rather than going linearly, which is very expensive. Everybody okay with this? Okay. So we're going to write a function that allows us to find whether a key, a value, exists within the tree. So the function I have in mind is something like this. First of all, we need to define a data type for that. So defining this data type would be something like this. Struct node t blah blah blah. Where is it? Int value, or if you wish, key. Okay, and then we have struct node t. By the way, this should be capital. This should be capital. Let me. Left pointer, struct node t, right pointer. And if you write it like that, now you have declared a data type, which is an aggregate data type. Aggregate means it's a collection of other data types that you have defined previously. Here, everything is an elemental data type. This is an integer. These are pointers. Pointers in C are really addresses. They're 32-bit quantities, which are meant to be interpreted as locations in memory. You can manipulate them as numbers because memory is a linear space. It starts from 0 and ends to 2 to the n minus 1, 4 gigabytes. So they have nice arithmetic properties, but they're addresses. They're not numbers, right? They're pointers. And there's this thing called pointer arithmetic, and we're going to see examples of that. Okay. Everybody okay with this? Okay. These elements? Yes. That's the intention. Is there anybody there to help you to make sure that this will happen? No. It's your job to make sure that it does, and this is where bugs come from. This is what you wanted to do, this is what you actually did, and then you're trying to find out what went wrong. Okay. There's nothing in the machine to help you. Alrighty then. Before we write f function, that searches this tree. Let's actually create that data structure in memory to see how it's being allocated. So I'm going to statically create that tree in memory. So I'm going to start writing that data stuff, and I will create an image in memory that will correspond to that data structure. You can do that programmatically if you wish. That is, you can write instructions that will create that image in memory. I believe before we even try to do that programmatically through instructions, it's important to understand what it's supposed to look like. So let's do it directly. Let's use the assembler to do that for us. We're going to say, please assembler, allocate memory and make it look like this. So let's, I'm going to call every node as node and the number. Sorry, I'm not coming up with interesting names, but I think it's more descriptive this way. So let's start with node 10. Okay, what is node 10? Node 10 is an aggregate data structure. It contains 3 sub-elements. Each one of them is 32 bits. The first one is meant to be interpreted as a number, a key for us. The other 2 are addresses, which in NEOS happen to be 32 bits. This is because of this machine. It could have been different. So we're going to be defining words. What is the first value? When you declare things like this in C, the compiler and the assembler takes this literally. First there's going to be a value, then there's going to be a pointer, then there's going to be another pointer. So this data structure in memory will look like this. At distance plus 0, you're going to have the value. At distance plus 4, you're going to have the left pointer, and at distance plus 8, you're going to have the right pointer. This could be anywhere in memory. The only thing you have to make sure is that if the value appears here, immediately after that you have the left pointer, and immediately after that is the right pointer. In a way, if I give you the address of where this is located in memory, by going a distance plus 4, plus 8, or plus 0, you can access each sub-element you want. That's the idea. Everybody okay with this? All right then. Let's go back to this. So first word here, we have to be the value 10. And after that, we need 2 addresses, which is where in memory we decide to store the left and the right child. Let's hold all of our horses for the time being. Let's write the other one, and then it will become clear how we can do that. Let's do node 5. And again, pointer, pointer. Let's do node 7. Which one should I do next? Yes?
Why are there 2 dashes?
Because we're going to fill them in later on. I'm just holding off for a while.
How are you choosing the order 10, 5, 7?
That's a good question. Which one would you like me to do next?
34.
34. See, he took over, okay? You snooze, you lose. Okay, 34. Okay, your wish is my command. Well, not always, by the way. 34. All right, which one you will wish us to do next? That's a 20. That's a good choice because I think that's the only one. No, it's not the only one. Good, you did have a choice and you used that wisely. My congratulations to you. 20. Am I getting a speed writing thing? Legibility award? Oh. Anyway, and for the grand finale, node 3. Alrighty now, what are these? Empty spaces. Some people are uncomfortable with empty spaces. In this case, we have to be uncomfortable because they have to be filled in with numbers. This is the left child of node 10, which happens to be node 5, okay? This is meant to be the address in memory where node 5 is stored at. How can we refer to that?
Label? Just right.
Node 5.
Node 5.
Yes, I know that's what you're saying, but they took over. Node 5. If I were to call this banana, I should have written banana. That's what it is. So don't read much into this being node 5. It's just a way to refer, to cross-reference. That's all there is to it. It's a sequence. Should I fill in the thingy? Okay. All right, so this would be node 20, node 5. node 3 and node 7. 7.
0, 0.
Okay. For some weird reason, you're absolutely correct. Okay. But why are you correct, though?
Because I'm good at this game.
Okay. That's one way. So somebody woke up one morning and said, how do we represent emptiness? All right? That is, there's nothing there. Okay? So if you really want to be pedantic about it, well, 0 is an address. All right? Why are we singling out 0 and saying, you can never have a pointer? We're sorry. That's what we're doing here. If you want to be pedantic, you have to have an extra field that says the pointer is empty. And only when that says it's not empty, here's the actual address.
What if your node 10 starts at 0?
Exactly. What if? It cannot. So it's like, I'll tell you why. It's a simplification. That's this whole story. So somehow we say to, look, there's 4 giga addresses out there. You come to them, you say, those that can actually have a pointer point to them, please step forward. Everybody does that, and 0 does that. And you say, oh, not so fast, node 0. You cannot have a pointer. Why? Well, somebody has to take one for the team. Why? Because this, that's why. It's really that. I mean, that just simplifies the code. You're saying, you know what, rather than having an extra field that says the pointer is not there, and then so that 0 can have a pointer, you say, 0, sorry, I'm going to reserve you, and this your special value, you cannot have a pointer. Do you want to put the pointer to 0? Yes, but you have to write your code so that it can follow 0. Okay. There are machines where, for other reasons, there are specific areas you cannot dereference, but NEOS is not one of them. You could have something at 0. It's by convention that 0 happens to be not a pointer. Okay, by convention. Everybody okay with this? All right. Can you fill in the rest? Save us the trouble. Okay, everybody feels comfortable with that? Okay, now, next question. Why did we put node 34 there? What's the answer to that? I mean, the obvious answer is because somebody said so, but that's exactly the reason why. I mean, that's, somebody said, let's put 34 here. 34 could have been here. 34 could have been on the other side of memory. 34 could have been anywhere you wanted. Why? Because this is a recursive data structure, and everything is by reference. You're just referring to it. You say, here's where you're going to find the other one. It could be anywhere you want. Node 10 does not have to be the first one here. It could be anywhere. All I need to do is, if I need to remember how to get into this tree, somewhere I need to remember that that's where node 10 is. Okay, that's all there is to that, right? That's the nice thing about recursive data structures. Now, what we've done over here is static allocation of everything. What you typically do in modern programs is you have these functions that allow you to get to dynamically allocate these things, okay, if you want to. Where we have to talk a little bit about how the whole system is built, that there's an operating system underneath that manages memory. You go to it and you say, oh, please, operating system, give me some space I can use. It gives you some space, and then you can freely allocate stuff over there. I don't think it's the right time to do this kind of stuff. But this is eventually, you have to create that image. As I said, here we do it by hand directly, by asking the assembler to do it for us. You could have done this programmatically by asserting instructions there and saying, write this value to this memory, write that value to that memory. Behold, you can do anything you want. Okay, I think I'm mumbling now, so I'll stop. I think I need to take a breath. Okay, let's write down the function, which I don't think we're going to finish today. Let's see. Let's try. I mean, I'm sure I can finish it. I'm not quite sure anybody else will follow me. R0 is a register.
So it cannot
be an address. Addresses, memory, and registers are storage locations. They both have names. The names for addresses happen to be 32-bit quantities, which are linearly allocated, so you can treat them as numbers. Registers don't have numbers as names. They're called R0, that's why there's that R. And there's no instruction you can use to take its outcome and use it as a name to refer to a register. I don't know if this, I'm able to explain that. You could take the result of an addition. You can write this. You can say add I, R10, R20, and 30. You can write that, and then you can turn around immediately and say load word into R11, 0 from R10. Okay. This is a number here, right? However, it happens to also be a 32-bit quantity. I can use that to go to memory and say, give me something that's in that box. Make sense? Yes? Sorry, I don't mean to put you on the spot. I'm just asking so to know to move on. So here I use it as a name to go to addresses. There is nothing equivalent here where I can do this and then say there's an instruction underneath, and there is some way to say here whatever register I want to refer to was the result of that. There's no such way to refer to registers. There isn't. We may refer to them as 0 to 31, but they're not considered to be numbers. There's no way to express that in the computer we're using. Could you build a computer that has that? Yes. Is that a good idea? Probably not. We can understand that later on when we talk about performance optimization. But you could do that if you wanted to. You could. Will people find a use for it? Yes. Will that be a good thing? Probably not. Okay. Now, just give people enough so they can write what they need, and be very careful when you give extras, because you have to live with them for the rest of your life if you're building computers. If you look at the Intel processors, they have to live with stuff that people designed back in the 70s. There's a favorite story of mine. I mean, we have time. We can do this Wednesday. There is a, you know Unix, right? Huh? Linux is based on that. But do you know there is a Multics? Actually, there was a Multics. Actually, this is a pun on this. This came after that. Multics was the operating system to beat them all. I mean, I don't know what it was like, late 60s, early 70s. Don't quote me on that. I was a baby. No idea. So Multics had, anybody knows about Byzantium? It was like the continuation of the Roman Empire, the east side. So when you say something is Byzantine, how do you pronounce that in English? Thank you for that. Say that again. Byzantine. I'll try to remember. So it was after a while, and I want to say I will, but I'm not quite sure I will. After a while, nobody trusted anybody. So that term is often used for any kind of organization where everybody's suspicious of everybody else, and you have to instantiate processes so that things can be done. So Multics was something like that. It was an operating system where if you wanted to make a call and you wanted to write something on the screen, you have to ask the operating system, say, hi, operating system, I'm this. And then you had to prove that you were that. And then the operating system had to give you specific credentials so you can do things like that. So it was supposed to be a very, very safe and everything, blah, 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 blah. Long story short, everything became very complicated, and the whole thing was too complicated to build and to implement. When Intel was building the 286 processor, so there was the first machine was the 8088. So if you have an i7, i5, an AMD, Ryzen, whatever, they can still run this code. I mean, that's the core instruction set. The first was the 8088, and then this was 8-bit external interface, and then it was 8086. These are the first ones. And code that ran on those machines has to run correctly on machines that exist today. That's compatibility. Then there was a failed, not failed, there was a not commercially successful attempt to create a system on a chip at the time. So it's an 8086 processor plus some peripherals on the same chip. Never picked up on market share. And the next was this one, 286. It goes on. Then there was 386, 486. Then they started using names like Pentium and all this kind of stuff, right? Anyway, 286 among what they call microarchitectural optimizations, which are techniques at the circuit level or which are programming transparent that boost performance. It also added more instructions, and they keep doing that. Every time they come up with a new generation, they add instructions. 286, whoever built that, some of them actually read this, and they liked it. So there are instructions in there that implement stuff that has to do with this. When I was a first-year graduate student, I actually read some of that stuff. I understood a portion of it, and I was scratching my head. I don't know why somebody would implement that, but it was there. And I had an interest, and I learned it a little bit. Long story short, the processor you have today has to live with that. Who uses that? Am I writing this correctly?
Is this
Huh? Is that how it's written? Am I misspelling it?
Well, what are you trying to spell?
Haha, I'm sure this is correct. Vowel? Yeah, look, if it was like a legal procedure or my life depended on it, I would say I want to revisit my statement, but with you and I will say nobody actually uses that now these days. But it has to be there just because somebody might. Okay? Long story short, so when you build hardware, you just build as much as necessary to make sure that people can implement what they need. And then you're being very careful to add, sprinkle things on top of it so that you can help them implement things as fast as they need to or as convenient they want to. Okay? But not more than that. This is a balance, because what seems to be a good idea today might be a horrible idea a couple of years down the line, because it's extremely hard to predict the future. And I have tons of examples to give you if you want. There was a machine, I think, did I mention that could do polynomials? There was a machine that will do polynomials. There was a poly instruction. You could give powers of x that you want to evaluate, and it will do that. It also had a double linked list insertion instruction. That was a machine level instruction, right? Anyway, wonderful things. Anyway, let's finish this on Wednesday, right? And then we'll start talking devices. Now, I have to warn you a little bit. Function calls look simple, and they are, right? However, you have to play with them a little bit, right? If you want, I would suggest each one of you to try to implement some. I mean, your lab is going to help you a little bit, because you're going to have to write, basically it's like a BLT sandwich, right? You're going to have functions calling your functions, and your functions have to call other functions. Those you have no control over. You have to build the one in the middle. So you will have to work with those, and that's why the lab is designed the way it is. But if you want to practice a little bit on your own, try to implement something like add 7. I hope everybody's okay, but I'm going to ignore that. Okay? And try to implement that with something like this, like sum plus equals add 5, and pass 5 arguments to that, the first 5, and then after that do a sum plus equals add 2 if you wish. And you can play with these two numbers. Right? Use the first 5 here and the last 2 over here, because it makes it a bit more complicated. And then if you wish, flip it around. Use the first 2 here and the last 5 there to see what's going on. Try this. You can always try it on, I don't know, do you have access to the boards or not yet? Did they give the boards to you so you can take them home? No, I mean, they're actually glued on the... Huh? Yeah, I have no stake in the game on that. Do whatever you think is best. I think these boards are a little bit behind the times. Right? I think they're better boards now, maybe. I haven't really looked into that. But anyway, I'll be happy to go with whatever you write with you before. Again, this is not an issue of intelligence or not. This is just an issue of experience. It's like saying, can you drive a car? Of course you can. You just have to put the hours in. This is one of those things. You may get it right the first time. More power to you. I didn't. Okay, so try it. And this is a good exercise. It's very tedious, but it will expose everything. Right?